All right, so I want to start by reviewing these Michaels reactions that we talked about last time. All right, so let's do this one first. We have this dial here where this alpha carbon is sandwiched between two carbonyl groups. We're going to treat that with a base and then add in an enone there. Okay? Our base is going to create an enolate ion. Now, importantly, because this is such a super stabilized alpha carbon, making it more acidic, we can get away with using something weak, like just NaOH. I guess it's not weak, it's like literally classified as a strong base. But in the context of organic chemistry, it's kind of on the weaker end of what we need to use here for our aldehydes and ketones. Okay? So everybody take a second and give me the Michaels reaction here that we see. So that dial is our nucleophile, specifically at which site here? That alpha carbon. And our enone, right? That was kind of our slang term for these alpha beta unsaturated aldehydes and ketones. We called them enones, is our electrophile. And specifically for a Michaels reaction, the whole shtick is that which one of these carbons is your electrophile? The beta carbon. All right, so in my product here, I'm going to have a new bond between that red alpha carbon of my nucleophile. I'm going to draw my new bond in. On the other side must be that blue beta carbon, my electrophile of my enone. All right, importantly, when I draw in my other carbons here, I'm going to lose that carbon-carbon double bond, but I retain that carbon-oxygen double bond. All right, so I got my carbonyl group, so just to color my carbons here so we can make sure we follow this. All right, my product has a total, whoops, I got too many going on here, my bad. Choo-choo. See, that's why we count carbons. All right, so my reactants have these 1, 2, 3 carbons colored in red here. And my products have also 1, 2, 3 carbons. We're going to color in blue. And I have that new bond between the alpha carbon of my nucleophile and the beta carbon of my Michaels acceptor. All right. Cool, so we talked about how our Michaels acceptors are kind of, or rather our Michaels donors, our nucleophiles, are kind of this limited category where we have to have these super stabilized carbanions. And so one common feature that we see is we have this alpha carbon sandwiched between two carbonyl groups, two electron withdrawing groups. So let's imagine that we try to do the same thing with just a normal old aldehyde or ketone, okay? Again, our first step, we need to create that enolate ion. But now, what kind of base are we going to use? Are we going to be able to get away with just NaOH? No, now we would have to use one of our really strong bases, like either LDA or NaH. All right, in this case, either one would work because there's only the one alpha carbon, but we did talk about how we could kind of tune your reaction conditions to be selective. All right, but now this enolate ion, let me just draw it. LDA after step 1, we'll have that enolate ion. But now this enolate ion is not super stabilized by 2 carbonyl groups. It is stabilized by the 1, but it doesn't have the 2. So this would be too strong of a nucleophile to react with our beta carbon of our Michaels acceptor. Instead, it would simply react with that other electrophilic site, our carbonyl carbon. All right, so instead of having a Michaels reaction here, you would just simply have your aldol addition reaction. Okay, for the sake of practice, take a second and give me my product of this aldol addition reaction. So I'm going to draw my nucleophile over. I'm going to color that alpha carbon, my nucleophilic site. When I draw my new bond, what's going to be on the other side of that bond? My electrophile. Okay, so let me fill in those other carbons here. Notice how we didn't touch that carbon-carbon bond this time. All right, what's the other thing that we'll always see when that carbonyl carbon gets attacked? What else do I need on that blue carbon? An OH group. All right, so you're trying to do a Michaels reaction and you take your aldehyde and you even waste your super strong base, your LDA or your sodium hydride. And what comes out the other side is not that Michaels reaction product, but just a regular old aldol addition. And you're like, oh crap, I really wanted a Michaels reaction, all right? Well, don't worry, Stork's got your back here, all right? We can do what's called the Stork enamine synthesis. All right, and this is just essentially a process to convert any aldehyde or ketone into a Michaels donor. Okay, so we had this very limited category of Michaels donors before. They all had that same feature of having those that one carbon flanked by those 2 electron withdrawing groups. So kind of this limited category. Well, it turns out that we can turn any aldehyde or ketone into a Michaels donor. All right, and it's actually pretty straightforward by converting it into an enamine. remember an enamine is that weird unexpected product that we get from the nucleophilic addition using a hydrogen nucleophile and our aldehyde and ketone. All right, so what we're going to do, we're going to take this same set of reactants here, but instead of treating it with a base, I'm going to treat it with a secondary amine. All right. And I gotta be honest, I've never done this reaction in the wild, so I'm not entirely sure why, but they do seem to have one particular one they like to use, which is this cyclic amine ring here. Now, importantly, after that first step, let's just remind ourselves what the heck I mean by an enamine. Actually, see if you can't tell me. All right, after that first step, we get an enamine. Kind of think about the name. All right, and this is true of any time we react an aldehyde or ketone with a secondary amine. So that nitrogen is going to replace that carbonyl carbon, and we're going to get this new carbon-carbon double bond that forms. All right, so let me just sort of be clear here and indicate where that formerly carbonyl carbon is in this step here. Right, your nitrogen will react with your aldehyde, where that nitrogen replaces the oxygen on that carbonyl carbon. And then you get this carbon-carbon double bond that forms, all right? We actually looked at the mechanism of this. For the sake of time, we're not going to do that again, all right? We have this enamine product, okay? I just wanted to color my alpha, or rather my carbonyl carbon orange here so that we could see who's who. Okay, the important thing here is that your enamine has a weakly nucleophilic alpha carbon. Which was the whole shtick, right? Which was the whole point of a Michaels donor, was having this weakly nucleophilic alpha carbon. So by taking this aldehyde, we're not going to create an enolate ion. That's too strong of a nucleophile. We're going to first treat it with a secondary amine to create an enamine, and now we have that weakly nucleophilic alpha carbon. Okay? And when we do steps 2 and 3 here, now because it's weakly nucleophilic, it's going to react with that electrophilic beta carbon. All right, and kind of the nice thing is that after that last step, after that acidic workup step, you kick that hydrogen right back off. So you're still left with your carbonyl group at the end. So in order to draw my product here, I'm not even going to worry about this little enamine intermediate here. I'm just going to take my aldehyde, and I'm going to create my Michaels product exactly like I did before, connecting that alpha carbon to that electrophilic beta carbon of my Michaels acceptor. we can just make note that that acidic workup in step 3 is what replaces the nitrogen back with that carbonyl group. So again, we can convert any aldehyde or ketone that we want into a Michaels donor by just, instead of adding base, adding in a secondary amine. That secondary amine will create an enamine, which has that weakly nucleophilic carbon. That's exactly what we need for our Michaels reactions. And so when we add in our enone, we get that nucleophilic addition to the beta carbon of that enone. All right, and we got one more reaction to cover in this chapter, and I'm not gonna lie, it's kind of a doozy here. All right, these are what are called Robinson annulation reactions. All right, so a Robinson annulation is a Michaels reaction. Followed by an intramolecular aldol condensation. Aldol, we're going to say aldol or Claisen condensation. All right, so our product of our Michaels reaction is going to, what do I mean by intramolecular? Like within itself, exactly, right? So this molecule is going to react. One end is going to react with the other to create this intramolecular aldol or Claisen condensation. One thing we can note is we're always going to get a 6-membered ring as our product. Okay, a helpful thing to keep in mind here when we're doing our reaction. All right, so let's do an example here. Again, first thing we need to do is do a Michaels reaction. All right, so this will just be review. We're going to take a nice stabilized Michaels donor here. We're going to treat it with some base. We don't even need to use anything crazy. All right, and then we're going to add in our Michaels acceptor. And then that acidic workup. Okay, so everybody take a second and give me my product of this Michaels reaction here. Whoops, and this one's the red one. Cool. All right, so we did our Michaels reaction, all right? And then we're going to take this product here and we're going to add in our reactants for our aldol condensation. All right, so NaOH. Okay, they typically carry these out in ethanol as well, so that's that solvent that we're going to use. Okay, and what we're going to see is, I'm just going to actually recopy this here to make a point, because we got our coloring that we used for our Michaels reaction. All right, we're going to want to switch up the coloring here. Okay. So when we do this, we're again going to see a aldol condensation here, all right? In our aldol condensation, remember we have an alpha carbon reacting with an electrophilic carbonyl carbon. But importantly, these are always going to produce these 6-membered rings. So we need this like perfect spacing here. So if we identify our alpha carbon, in this case, this molecule is symmetric, so I could pick either one. Okay, this will react with a carbonyl carbon as long as it's got that perfect 6-carbon spacing. All right, so if we start counting here, 1, 2, 3, 4, 5, 6. We can see that indeed that carbon, that alpha carbon, is going to react with this carbonyl carbon right here, right? And it's going to be this super big, ugly product, but it's just the same mechanics that we've already studied before of our aldol condensation, all right? We've sort of seen this before when we had our Diels-Alder. In this case, this molecule is kind of already kinked in such a way that I think I can pretty easily see how that ring is going to form. That's not always going to be the case, right? These single bonds just happen to already be bent in the way that we want them to be bent. But sometimes it's kind of hard to twist around single bonds in your mind. So I think one of the easier things to do, and we did this before with our Diels-Alder, which also made rings, is to start with that ring and then to number. All right, and just make sure that you then decorate it with everything that needs to be decorated, right? So what do I mean by that? Well, on carbon 3 on my reactant side, I have that whole like aceto group. I'm going to put that on there. What about on carbon 2? There was a carbonyl group. Was that carbonyl group involved in this reaction at all? It wasn't my nucleophile. It wasn't my electrophile. That thing didn't get touched. So I'm going to include my carbonyl group on carbon 2. I got an isobutyl group on carbon 4. Put that thing in there. Right? Now in the aldol, okay, and then just to be clear, let me do my coloring. The 1 was our nucleophile, 6 was our electrophile, okay? In an aldol addition reaction, we have that OH here. All right, but in these Robinson annulations, because they are this internal rearrangement, you actually always get the condensation product, which is, remember, the addition followed by that dehydration, right? So we're never going to have our OH in our product here. Instead, we're going to have that carbon-carbon double bond. All right, and remember, it will always form conjugated to your carbonyl group. Let me move these over here. All right, so this is a Robinson annulation. We first have a Michaels reaction, and then we take that product and we do this aldol condensation reaction. All right, so obviously we get something big and ugly out on the other side here, right? Again, these are one of like probably the hardest reaction that we study in terms of just how big and ugly everything is. So you really want to break it down into the steps in terms of what we know, right? First step is that Michaels reaction where we connect our alpha carbon of our Michaels donor with the beta carbon of our Michaels acceptor, all right? And then we're gonna take that product and we're gonna look for an alpha carbon that is spaced exactly 6 carbons away from an electrophilic carbonyl carbon, right? And then we're just gonna do our normal old aldol addition reaction, or rather aldol condensation reaction, one that creates this 6-membered ring here. All right, so let's do another one. All right, I want you all to try to do this one on your own. Okay, so here's my Michaels addition product. But now I'm going to take my product here. I'm going to need to do new nucleophile and electrophile. Now we're going to do our Robinson annulation here. All right, so everybody take a second. Based on what we discussed before, see if you can't give me the product here. Okay, again, we need an alpha carbon that is located exactly 6 carbons away from an electrophilic carbonyl carbon in order for this Robinson annulation to occur. All right, so this one is not like perfectly kinked in the way that we can see what's going to happen like the other one was. All right, and importantly, we have a few different options for our carbonyl carbons and our alpha carbons, right? In particular, this molecule has 2 alpha carbons and 3 carbonyl carbons here, right? So I got to figure out which one of these has that perfect 6 carbon spacing. All right, so let's just start going through and see if we can't narrow this down. All right, these 2 are right next to each other. Those are obviously not going to react. Okay, what about these 2 here? These are spaced 1, 2, 3, 4 carbons apart. Not going to happen, right? I need that perfect 6 carbon spacing. What if I choose this alpha carbon and that electrophilic carbonyl carbon? That's 1, 2, 3, 4. All right, that one's not going to work. All right. If I choose this one here, 1, 2, 3, 4, 5, 6, boom. Got it. That's going to be my 6-membered ring right there. Okay? And again, these are now my single bonds are not rotated in a way that makes it super easy to see what my product should be. And you could totally just rotate about those single bonds on the page. That would absolutely work, but sometimes that's not so easy to do in our head. So again, what I think is the easiest thing to do is to start with what you know, which is that your product is a 6-membered ring. And we're just going to start numbering that ring and then filling in. All right, so given what we discussed, I want everybody to see if you can't finish off, if you've already done it, great. But if you hadn't gotten to this point, take a minute and see if you can't, based on this now, complete our product here. All right, so that second carbon has this carbonyl group. It wasn't involved in that reaction at all, so I know it's just going to remain a carbonyl group. Carbon 3 had this aldehyde sticking off of it. I'm going to put that on there. And I also need to include that methyl group that's sticking off of carbon 4. Okay? Now, since carbon 6 was my electrophile in this reaction, that carbonyl oxygen got converted to an OH. But again, in this case, we're never going to get our addition product, but rather we're going to get our condensation product, where we have that carbon-carbon double bond that's formed. All right, so this is my Robinson annulation product here. What's up?
Is the pi bond that's created always between carbon 1 and 6, or is that just...
It is in the case of when you have an aldol condensation. Yes, absolutely. It can be aldol or Claisen, all right? So depending on what we use as our electrophile. So we're going to do one more example here where that won't be the case, and we'll see why, okay? But yes, if we do have an aldehyde, or if it's just a regular old carbonyl carbon instead of an ester carbonyl, you'll get the double bond between carbons 1 and 6. Okay, so my caveat here was we could also do this reaction. Where instead of starting out with a ketone or aldehyde, we're going to start out with an ester. Okay, for the sake of time, I'm going to just quickly put down our Michaels reaction product. Yes, let me be good with all these lone pairs. Okay, but now I want you to importantly take that Michaels product and do our Robinson annulation. And again, I just want you to keep in mind that since we're starting with an ester here, we're going to get not an aldol condensation, but a Claisen condensation. And I just want to say, I know that I'm saying aldol and Claisen, and everybody's like, I don't remember that crap. I don't bother to remember that stuff. I'm just trying to look at the two reactants and figure out what the product is. I will say that for me as an instructor, I have to have those little bins in my brain in order to organize stuff. It helps me to remember the name of the reaction, because then I keep it in its own little separate category that's different from the other reaction categories. So it seems like it's more information, but what it really is more context for your brain to hold on to all that information, because it's a lot, right? So we need to kind of sort it out in our mind into little bins. And so remembering the names of stuff can be very, very helpful in that sorting process. Oh, I messed this up. We got one more methyl group coming off here. Hold up. Rewind. Currently, that one wouldn't. We don't have anything with our perfect spacing here. We were supposed to have an extra methyl group on here. Okay, my bad. Everybody take a second, copy that. I know I messed that up. Everybody take a second, recopy this. To be clear, all I did was tack on a methyl group right here, that orange carbon. that we need an alpha carbon that is 6 carbons away from an electrophilic carbonyl carbon. And so we have these 1, 2, 3, 4, 5, 6 carbon spacing here. All right? So my electrophilic my nucleophilic alpha carbon is going to attack that electrophilic carbonyl carbon. Okay? I'm going to start by redrawing my 6-membered ring. Okay. Let me put in that extra stuff real quick. We have this ester group off of carbon 5 and a methyl group off of carbon 4. Okay. Now, importantly, in this reaction, we haven't been doing mechanisms, but we have seen these mechanisms before. The first thing that we get is that tetrahedral intermediate. And for aldol addition reactions and condensation reactions, you get a tetrahedral intermediate, and you always ask yourself, what for a tetrahedral intermediate? Is there a good leaving group? And for aldol addition and condensation reactions, the answer is no. So the only thing you can do is protonate that oxygen. But for Claisen addition and condensation reactions, we do have a good leaving group, right? That ester methoxy group in this case is going to play the role of a leaving group. So in our product here, we're not going to have a carbon-carbon double bond. We're going to reform that carbonyl group on carbon 6. So this is now a Claisen condensation, an internal Claisen condensation. So at the end of the day, we reform our carbonyl group, giving us, oh crap, and, geez Louise, I'm already on break. All right, we forgot another one on carbon 2. We didn't lose that guy. So these Robinson annulation reactions are going to be kind of a pain in the butt unless you really take them step by step and count your carbons carefully. All right, first you're going to do that Michaels reaction to create this Michaels product where that nucleophilic alpha carbon is connected to the beta carbon of the Michaels acceptor. And then you're going to try to find an alpha carbon and a carbonyl carbon that have this perfect 6 carbon spacing. And you're going to link them together in either an aldol condensation or a Claisen condensation reaction. So this will be a fun thing to practice, you know, fun party trick over your Thanksgiving break here. Show your family everything you can do in organic chemistry. Cool. Enjoy your break. Yeah. No, that Monday, we have a full week of lecture before then. The next week is when your exam is.
When we did the first couple of examples, and you said that it's either like a weak nucleophile or a strong nucleophile,
Yeah.
like which one? Okay, how do you know which one's weak?
So this one's weak because it's stabilized by both groups. This one is not as weak because it's not as stabilized, right? So this negative charge is more angry than this negative charge.
Okay.
This charge is like, fine, I'll be here, I'm stabilized on both sides. This one is not.
So it's like the ones that we were doing where it's these, that are the alpha carbons between 2 carbonyl groups.
Are all Michaels donor because they're super stabilized weak nucleophiles. Yep.
Okay. Whereas those ones aren't because they're not stabilized. Just like if they're by themselves.
Well, these are the acceptors, right?
Oh, yeah.
So the examples, there are two examples that we talked about of the really strong ones. The regular enolates, the ones that aren't stabilized on both sides, but just one side, as well as like a Grignard is another strong nucleophile compared to the Gilman, which is the weak nucleophile.
Okay. That makes sense.
Yep.